Section 8.2 Infinite Series. In this section, we are going to define an infinite series as the limit of a special type of sequence. We then study a few basic properties of infinite series and examine geometric series, a particular kind of series with numerous applications. To have an idea of infinite series, let's consider one of the paradoxes of Zeno. Suppose Homer wishes to walk to the end of a path. Before he can get there, he must get halfway there. Before he can get halfway there, he must get a quarter of the way there. Before traveling a quarter, he must travel in 1/8. Before an eighth, 1/16, and so on. It turns out that you can actually get anywhere because you always have to cover half of the remaining distance. You have to do half, then half that, etc. In mathematical language, we say that the distance he has traveled is the sum of numbers starting from 1/2. A successive number is half of its predecessor. This sequence is infinite and the terms are always positive. So, that it makes sense to add infinitely many numbers. The answer is yes. In mathematics, such sums of infinitely many numbers are called infinite series. So, in simple language, a series is a sequence added up. One way to add a list of numbers is to form subtotals until the end of the list is reached. Let Sn be the partial sum of nth first terms from A1 to An. If the sequence of partial sum approaches a limit, as n increases without bound, then the associated infinite series has a sum equal to that limit. So, the series is said to converge with some s if the sequence of partial sum Sn converges to S. We take an example. Consider the infinite series sum of 1/2 to the power of k for k from 1 to infinity. The first term occurs when k equals 1. So A1 equals 1/2. The second term occurs when k equals 2. So A2 is 1/4. Similarly, the third term is 1/8, etc. We form partial sums of this series by adding up nth first terms. The first sum S1 includes only the first term 1/2. The second sum S2 includes the first term 1/2 and the second term 1/4. The third sum S3 includes the first term 1/2, the second term 1/4, and the third term 1/8. The fourth sum S4 includes the first term, the second term, the third term, and the fourth term 1/16. In this series, each term is 1/2 the preceding term. Every series that has the property that the ratio of successive In this series, each term is 1/2 the preceding term. Every series that has the property that the ratio of successive terms in the series is constant is given a special name. A geometric series is an infinite series in which the ratio of successive terms in the series is constant. In this ratio, if this constant ratio is R, then the series has the form sigma of A multiplied by R to the power of K for K from 0 to infinity. The following theorem tells us how to determine whether a given geometric series converges or diverges, and if it does converge, what its sum must be. The geometric series sigma A R to the power of K for K from 0 to infinity diverge if the absolute value of r is greater than or equal to 1, and converge to a divided by 1 minus r if the absolute value of r is less than 1. To find the sum of this infinite series, we compute the partial sum Sn equal a plus ar plus etc. plus ar to the power of n. Multiplying this sum by r gives ar plus etc. plus ar to the power of n plus ar to the power of n plus 1. We take the difference between Sn and Rsn to obtain 1 minus r multiplied by Sn equals a minus a multiplied by r to the power of n minus 1. So, Sn equals a minus a r to the power of n plus 1 over 1 minus r. We take the limit of Sn when n increases without bound. It equals to lim when n tends to infinity of a minus a r to the power of n plus 1 divided by 1 minus r. This limit exists only when r to the power of n plus 1 converges to 0 and its value is a divided by 1 minus r. This happens if and only if the absolute value of r is less than 1. Otherwise, the sequence of partial sums diverges, and so is the series. We shall apply the theorem to find the sum of the series sigma of 2/3 to the power of k for k from 0 to infinity. This is a geometric series with a equals 1 and r equals 2/3. Since r is positive and is less than 1, the series converges and its sum is 1 over 1 minus 2/3 equals 3. We take another example. Compute the sum of the series sigma k from 0 to infinity of 1/2 to the power of k. This is geometric series with a equals 1 and r equals 1/2. It includes the terms beginning from 1 and each term is 1/2 of the preceding term. Since r is positive and is less than 1, the series converges and its sum is 1 divided by 1 minus 1/2, which is 2. What happens if the series starts from k equals 1? We see that the first term is now 1/2 instead of 1. To find its sum, we must subtract 1 from the sum of the above series. The sum of this series is 1. The second series shows Zeno's paradox we have mentioned previously. Although infinitely many terms are added up, their sum is exactly 1. We are going to apply geometric series to find a variety of sums. First, find the sum from k equals 2 to infinity of 4 multiplied by 2 to the power of k plus 1 divided by 3 to the power of k. We realize that by separating 2 from 2 to the power of k plus 1, we can write the series as a geometric series with a equals 8 and r equals 2/3. Note, however, that k starts from 2. The geometric series sigma k from 0 to infinity of 8 multiplied by 2/3 to the power of k equals to 8 plus 8 multiplied by 2/3 plus sigma k from 2 to infinity of 8 multiplied by 2/3 to the power of k. Since the absolute value of r is less than 1, its sum is 8 divided by 1 minus 2/3 equals 20. The series from 2 to infinity can be found by subtracting the first two terms, 8 multiplied by 2/3 from 24. The result is 32/3. We consider another example. Find the sum of the infinite series sigma k from 2 to infinity of minus 1 to the power of k multiplied by 4 to the power of k plus 1 divided by 5 to the power of k minus 1. This series is called alternating series because the signs of the Echelon terms alternate between positive and negative. Separate a factor 4 from the numerator and multiply 5 to the denominator. We get a geometric series with a equal 20 and r equal minus 4/5. This series starts from k equal 2 to the power of k equals to 20 plus 20 multiplied by minus 4/5 plus sigma k from 2 to infinity of 20 multiplied by minus 4/5 to the power of k equals to 20 divided by 1 minus 4/5 equals 109. The series from 2 to infinity can be found by subtracting the first two terms from 109. The result is 64/9. Now we consider the series sigma k from 1 to infinity of 7 multiplied by 3 to the power of k divided by 2 to the power of k minus 1. Multiply the denominator by 2 and write the given series in geometric form with a equals 14 and r equals 3 seconds. Since the absolute value of r is greater than 1, the series diverges. We end this section by an example about telescoping series. A series is called a telescoping series or collapsing series if there is internal cancellation in the partial sums, as illustrated by the following example. Find the sum of the series sigma k from 1 to infinity of 1 divided by k multiplied by k plus 1. We use partial fraction to find partial to express each term as We use partial fraction to find the way to express each term as 1 divided by k minus 1 divided by k plus 1. The partial sum Sn is 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus etc. plus 1 divided by n minus 1 divided by n plus 1. By cancelling out the common terms, we obtain 1 minus 1 divided by n plus 1. By definition, the series sigma k from 1 to infinity of 1 divided by k multiplied by k plus 1 is the limit of the partial sum Sn as n increases without bound. It equals to 1. This is the end of this session. Thanks for watching.